Okay, let's start. Where are we now? Let's go back to the first page of this chapter. Okay. In the last lecture, we have learned what is the low reduction and echelon form. Actually, we learned the definition of the echelon form and the definition of the reduced echelon form. So reduced echelon form is called the REF. Echelon form is called the EF, like this. And we also learned what is the pivot position and what is the pivot column. Okay. So yeah, let's see the example. As you can see here, the pivot position in a matrix A in a location that corresponds to a leading one in the reduced echelon form of matrix A. Okay, let's say we have a original matrix A and we convert this original matrix A into the reduced form, something like this, right? So in this reduced form, there is a three leading entry here. So this position is called the pivot position of this matrix. And what is the pivot column? The pivot column is the column of a matrix A that contains some pivot position. So in this case, so this one, and this one contain the pivot position. So these three columns are called the pivot column. Okay, so this is the definition of the pivot position and pivot column. And actually, the last lecture I gave you some example, something like this, right? But there was some mistake on this example. Okay. Question: is this matrix is reduced echelon form? Okay, let's rewrite again. Is this matrix is reduced echelon form? No. Why? Because this one. Because of this one. Because in the definition of the reduced echelon, because the definition of the echelon form, there is the condition 2 like this. So this condition makes the echelon form matrix looks like this, right? But in this case, there is the leading entry here, right? So this matrix no more than the echelon form, right? So to make this matrix as a reduced echelon form, we can replace these two rows like 1 0 0 1 0 0 5 0 1 12 0 0 something like that, right? So this is the reduced echelon form, right? Okay. In this case, what is the pivot position? So pivot position should be here, right? Then what is the pivot column of this in this example? So these two columns should be pivot column. Okay. So this is the examples of the pivot position and pivot column. Okay. And then why does pivot position when we use the pivot position to solve the linear system? Okay, let's see the example. Okay, if we have the matrix A, something like this. So first of all, we can make this matrix A into the echelon form, and then we can find the pivot position of matrix A in the echelon form, like this. So by using the elementary law operation, we can reduce this original matrix into the echelon form, something like this, like this, like this, right? So as you can see here, this is the like this. So this is the this matrix is called the echelon form of the original matrix A, right? So this is the echelon form matrix A. So finally, there is a pivot position like this, and there are 3 pivot columns, right? Why is that important? First of all, pivot position is the pivot position can be determined on the fixed position of each matrix. So it means that it contains some information of the matrix, and so pivot position tell us where is the solution exists or not. Okay, we can see this today. Okay, so it was the definition of the pivot position, something like that. And finally, the last lecture, in the last lecture we also learned the low reduction algorithm, or called the Gaussian elimination, like this. So what was that? So where is the examples? Yeah. There is a summary of the low reduction algorithm. So they're consisting of the 5 steps, right? So from the original matrix A, we use the elementary law operation to convert the original matrix A into the echelon form of matrix A, like that. So it was the step 1 through the 4, and in the step 5, we produce the reduced echelon form, reduced echelon form of the original matrix A. So this is called this step's called the backward page, and this is called the forward page. Okay, so notice that for each matrix A, there's only unique reduced echelon form, right? So if the original matrix A is changed, the reduced echelon form also should be changed, and there is only single unique reduced echelon form of each matrix A. Okay, so it was very important theorem, right? So like this, right? So okay, so let's say we have a matrix A that we want to solve, and we use the R low reduction algorithm, and make this matrix as a reduced echelon form, like this. Okay, we have a reduced echelon form of the original matrix A. Then what does this matrix tell us about the matrix? This reduced echelon form of the matrix tell us what is the solution of the matrix, and there exists the solution or not, and the solution is unique or not. Okay, so let's see the detail. So this is a reduced form of the matrix A, and we can go back to the equation form like this, right? Now you can easily convert the matrix to the equation, or equation to matrix, right? So So this, because this is the augmented matrix, so we can write the x1 minus 5 times x3 is equal to 1, x2 plus x3 is equal to 4, 0 is equal to 0, right? So in this case, what is the solution of this linear system? What is the solution of the linear system? Okay, we can rewrite the x3. Okay, we want to find the x1, x2, x3, right? So to get this solution, we can rewrite the x3 is equal to x3, x2 can be represented by a parameter x3 like the 4 minus x3, right? Like this, right? So x1 is equal to 1 plus 5 times x3, like this, right? So from this linear equation, from the modified form of the linear equation, we can say that if x3 is equal to 1, x1 and x2 should be like this, and if we choose x3 as a 2, x1 and x2 should be like this, right? So it means that it's gonna be infinitely many solutions as varying the parameter x3. Okay, so there is a definition. So okay, in this case, the variable x1, x2 corresponding to pivot column in the matrix. What was that? In this case, what was the pivot column? Here and here, right? So because each column corresponds to x1, x2, x3, right? So in this case, x1 and x2, variable x1 and x2 are called basic variable. What does that mean? So the values of the basic variable can be determined via another free variable. Then what is the free variable? The remaining variable or the other variable. In this case, x3 will be the free variable, right? So here's the definition. So if we reduce the original matrix A into the reduce this matrix A into the reduced echelon form like this, we can determine what is the basic variable and what is the free variable with the pivot position, pivot position or pivot column, right? So it means that by using the free variable and basic variable, we can determine the solutions of this linear equation. Okay. So here's the thing. So whenever a system is consistent, the solution set can be described explicitly by solving a reduced system of the equations for the basic variable in terms of the free variable. Okay? What does that mean? Okay, let's go back to the basic. What is the consistent mean? What makes the system consistent? Consistence was related to the existence, right? Existence, right? If the system is consistent, there is a solution. There exists a solution for that system, right? So in this case, we can reduce the original matrix A into the reduced echelon form, or call the reduced system of equation, and we can determine what is the variable and what is the free variable, and then we can solve this linear system in for the basic variable in terms of the free variable, like this. Okay, this is what we want to do. And so this operation is possible because the reduced echelon form places each basic variable in one and only one equation. What does that mean? What does that mean? The reduced echelon form, here there is only one single variable at each row. Okay. There is a 3. Okay. Let's name. In this case, there is 3 row like this, and at each row there are single variable, right? Single basic variable, right? With what? With free variables. Okay. So it means that we can represent this equation for the basic variable with what? Free variable, right? So let's go back to the example here, right? So we already do that, right? So how can we represent this? We could say that, okay, this one and this one is the pivot position. So we can represent this one and this one in terms of this free variable, right? So x3 is free or free variable, and x1 and x1 is equal to 1 plus 5 times x3, right? And x2 is equal to 4 minus x3, something like this. So in this case, the statement x3 is free means that you are free to choose any values for x3, right? Like this, okay? So this is the concept of the basic variable and free variable. Okay, so whenever a system is consistent and has a free variable, the solution set has many parametric description. What does that mean? Okay, so we can say that this we can say that this is the parametric description of the system or solutions of the system. Okay, this is a parametric description, but actually this parametric description is not unique. I mean, there would be many kinds of parametric description of the single linear system. What does that mean? Okay. Here is the same example like this. From this example, we represent x1 and x2 in terms of x3, right? They like this. Blah 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 blah. They like this, right? But if we use the other operation, we can represent x1 and x3 in terms of x2, right? Like this. Let's see the example. Here, okay, let's say this is equation 1, equation 2. If we just okay, in this equation we want to remove this part, and how can we do that? Equation 1 plus 5 times equation 2. So in this case, it makes another term like the 5 times x2, and we can remove this one as a 0, right? And 1 plus 4 times 5 is equal to 21, right? So we can represent this linear equation looks like this. Okay, so in this case, we can represent the x1 is equal to 21 minus 5x2, and x3 is equal to 4 minus x2, and x2 is, okay, let's use another. x2 is, okay, it's 3. Like this. Okay. So comparing to this parametric description, in this parametric description, we can represent this x3 and x1 and x3 in terms of x2, right? So this will be another parametric description of the solution set, and there will be another possibility, right? But so we could say that we could treat the x3, x2 as a parameter and solve for x1 and x3 in terms of x2, right? So in this case, we would have create a description of the solution set, right? So, but in general, we want to have a common rule or general rule, right? So generally, we represent the basic variable in terms of free variable. Okay, we can represent in a different parametric description, but generally we want to represent the parametric description as a basic variable in terms of free variable. And what was the basic variable? Basic variable are the variable that corresponds to the pivot columns in the matrix. Okay, so I would say we can represent this the parametric solutions of this matrix as a basic variable in terms of free variable. Okay, so the one more last concept, this is also very important theorem. It is called the existence and uniqueness theorem. Okay, what is that? Okay, let's see. So a linear system is consistent if and only if the rightmost columns of the augmented matrix is not a pivot position. So what does that mean? In other words, if and only if the echelon form of the augmented matrix has no row of the form like this. So if if the matrix satisfy this or this condition, the linear system is called consistent. Okay. So linear system is called consistent. Here is the example. Okay, we have a reduced. No, we just have the echelon form. Echelon form the matrix like blah 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 something like this, but there was the row something like 0 0 0 0 0 1 something like this. If we have the echelon form of the matrix like this, what is the last row mean? We can represent this last row as an equation form like x0 times x1 plus 0 times x2 plus 0 times, let's say, x6 like this is equal to 1, right? In other words, because this is only 0, right? It means that 0 is equal to 1. What is that? What makes 0 is equal to 1? It doesn't make sense, right? 0 cannot be equal to 1, right? So it means that there is no solution. No solution. Okay? So this theorem means that if there is no row like this matrix have the solution, so this linear system is called the consistent, right? Because this matrix anyway have the solution, right? So if you remember the last week's lecture, if the linear system is consistent, then the solution set contains the there are two possibilities of the solution set. The first one was the unique solution, where there are no free variable, and infinitely many solutions when there is at least one free variable. What does that mean? Okay. We have a matrix that we want to solve, and by using the row reduction algorithm, we reduce this matrix as a echelon form. Okay, echelon form of matrix A. And in the echelon form of matrix A, we can determine there is solution set or not. How? By using this theorem. Okay. By using theorem 1, we can determine this system is consistent or not, right? So it means that there exists a solution set or no solution set. Okay, so using theorem 1, we can determine this original matrix have the solution set or not, right? And if if this echelon form of the matrix doesn't have the any row like this, this echelon form of the matrix or the matrix original matrix A has the solution. So it means that we can represent the solution set using this parametric description like this, right? So in this case, okay, if there is a solution, we can represent the solutions of this matrix A as a parametric solution. And if there are no free variable in the parametric description, it means that there is unique solution. And if there is at least one free variable, we can say that there are infinitely many solutions, like this example. Because we can determine any values of the x3 and x1 and x2 will be determined by this free variable x3, so there will be the infinitely many solution, right? So there is the two case, and from the so it means that from this echelon form of the matrix we can determine this solution has the unique solution or not. We can determine this solution is unique or not. I can just say not. Okay. Okay. So actually these two kinds of question, consistent and uniqueness, can be determined by using a echelon form of the matrix. So this is that's why we learn the echelon form of the matrix. We can determine the property of the original matrix A using based on echelon form of the matrix. Okay. So okay, let's go back to the previous. Yeah, let's go back to the previous example. So, okay, let's say we have a matrix A, something like this. So, we want to solve this linear system, and but first of all, we want to know this matrix have the solution related to the existence, right? And if there is solution, the solutions is unique or not? Uniqueness, right? We want to answer these two questions of this matrix A. Okay, so how can we do that? First of all, we need I told you we need a reduced form of the we don't need the reduced form of the reduced echelon form. We just need the echelon form of matrix A. Okay, to determine existence and uniqueness. Okay, so where is the echelon form of the matrix A? We use the several sequence of the elementary law operation, right? Like this, something like this, right? So finally, we get the echelon form of the matrix A. right? We get the echelon form of the matrix A. Then based on this echelon form of the matrix A, the solution is consistent. The solution set exists or not, or the system is consistent or not. Consistent. Or solution is exist. Why? Because in the echelon form there is no law like 0, 0, 0, some kind of value. Let's say using the x. Because there is no law such as like this, we can say that this matrix has a solution, right? Then how can we so the next question is, the solution is unique or not? Then how can we do that? We have to find the parametric solutions of this matrix. So we need a reduced echelon form like this, right? Reduced echelon form like this. In this case, this one is a pivot column, right? I got pivot column, right? So in this case, this x1, x2, x3, x4, x5 variable. So in this case, what is the basic variable? The basic variables are x1, x2, x5. Basic variable. And what are the fixed variable? x3, x4. Of course, fixed. What was that? No, it's not a fixed. Sorry, the free variable. Okay. So what is the parametric description of this system? Let's use the red color and blue color for the free variable. Okay, so x1, x2, x5. So x1 is equal to minus 24 plus 2 x3 minus 3 x4. Okay, then x2 is equal to what? Minus 7 plus 2x3 minus 2x4, and x5 is equal to just 4, right? Because there is no non-zero values on the x3 and x4 positions, right? Then x3 and x4 is equal to what? Is just free. So x1 and x2 can be represented by the variable x3, x4, x3, x4, something like this. So this is a parametric description of the solution. So Okay, this representation tells us there are infinitely many solutions of this system. So instead, we can say that the solution set is not unique. Solution set of this system is non-unique. There are infinitely many solutions. Many solutions. Okay. So this is the existence and uniqueness of the system. Okay. Okay. Let's summarize the solving a linear system. Okay. To solve the linear system, we learn the low reduction algorithm, right? And we learn the how to represent the solutions of a matrix in a parametric solution, parametric description, right? So there is 5 steps. So first of all, if we have the equations of the linear system, first of all, we should write the augmented matrix of the system, right? Let's say like the A, right? And using a low reduction algorithm. Low reduction algorithm was like this. It consists of the step 1 through the step 4, which are called which are called the fourth step, and the step 5, which is called the backwards phase, right? So it was the low reduction algorithm. And we use the low reduction algorithm to obtain the equivalent augmented matrix in a echelon form, right? So we could say that echelon form of matrix A. From the echelon form of the matrix A, we can decide whether the system is consistent. It is related to the solution existence, right? So existence. If there is no solution, just stop, because we cannot find any solution from this linear system. Otherwise, go to the next step, okay, to find the real solution, and continue low reduction to obtain the reduced echelon form. Okay, so it means that using the fourth phase of the low reduction algorithm and use the backward phase of low reduction algorithm to get the reduced echelon form. Okay, so it is called the reduced echelon form of matrix A. Okay, so if we get the reduced echelon form of the matrix A, we write the system of equations corresponding to the matrix obtained in the step 3. So this is a reduced echelon form of the matrix, right? So from the system of the equation, we can determine what is the basic variable and the free variable. Then we can represent the solutions of the system as a what's the name of that? What was, where is, yeah, parametric description. So parametric metric description of solution. Okay, so from the parametric descriptions of solution, we can determine the solution set are unique or not. If there is the free variable, there exists the infinite many solution, and if there is no free variable, there is only single solution. Okay. So this is the last example of this section. Okay. The question is to find the solution set from this original equation, like this. So you can just follow these steps to solve this linear system, right? So from this linear system, what do you want to do? First, we should reduce this linear system as a echelon form, right? How can we do that? First of all, remove this one. Then, so let's say this is R1, this is R2. Then how can we do that? R2 will be the R2 plus 2 times R1. Okay. Then in this case, R1 remains unchanged, and R2 should be negative 2 plus 2, 4 plus 6, 5 minus 2, 6 plus 8, like this. It should be 1, 2, negative 4, negative 1, 4, 0, 10, 3, 40, right? Is that correct? No, it should be 4. Yes. So it should be A, something like this. Okay, so this is the echelon form of the matrix. Actually, we can go further, but from here we can just decide this system is consistent or not. This system is consistent because there's no law like this. So it means that this system has the solution set, and from this echelon form of the matrix A, we can represent the parametric description of the solution set like this. Okay, first of all, what is the basic variable and what is a free variable? Because these two columns are pivot column, you can do further to get the reduced echelon form of the matrix. Please do yourself, right? Anyway, we know that this is these two columns are pivot columns, so we can say that x1 and x2 are base variable, and x3 is free variable. Okay, so then how can we do that? Actually, we can go further to eliminate this part. Just represent the variable x1 in terms of x3. Okay? Then how can we do that? How can we do that? We can just R1 will be the R1. How can we do that? Minus 1 over 4 times R2. It will eliminate this one. Okay? Then it will be the 1, 1, 0 minus negative 7 over 4, 1 over 2, 1, 8, 3, right? Okay, so actually I'm not sure these values is correct or not, so please do it yourself. Okay, anyway, okay, if we get this matrix looking like this, then finally we can represent x1 is equal to 1 over 2 plus 7 over 4 x3, and x2 equals what? 13 over 8 minus 3 over 8 x3, and we can say that x3 is free. Okay, so this is parametric description of the solution set of the original matrix A. Okay, so from this description we can say that there exists the infinitely many solutions because there is the free variable. Okay, so this is the solving a linear system. Okay. Okay, this is the end of this section. From the last week until this week, we have learned how to define the linear system and how to learn how to solve this linear system in a systemical way. Okay. From the next week, we will learn what is the vector and what is the matrix and what is the independence of the linear system.